Let's get going. We're going to go ahead and start today by doing another couple of redox problems. We're going to be looking at reactions. We're going to be taking a look at oxidation numbers within those and see if we can figure out what's happening in the reaction. Just so we have kind of a formal definition, if any oxidation number changes during a reaction, it must be a redox reaction. And, you know, I say any, but really we have to have two changes going on, right? We need an oxidation and a reduction. We have to have both. So those two must happen simultaneously. Something has to be getting electrons and something has to be losing electrons. You can't just lose electrons into nowhere or just get electrons out of nowhere either. So just be aware of that. So if something is oxidized, at least one thing must be reduced. You're going to see that sometimes you can have multiple oxidations happening in one reaction or multiple reductions happening in one reaction, but you have to have, if it's a redox reaction, at least one of each. One oxidation, one reduction. You can have more. You can have 3 oxidations, 1 reduction, that's fine, but at least one of each for it to be redox. So let's go ahead and take a look at a few problems. So let's start by doing, let's do a combination reaction. Remember, for redox stuff, you do not need to balance them. So save yourself some time. If we want to determine if this is a redox reaction or not, we know this is a combination. But is this redox or not? We're going to see that sometimes combinations are redox, sometimes they aren't. So with certain reactions, we can see that they're always redox or always non-redox, but combination and decomposition could be either. So if we take a look at this, let's see what's happening. Well, if we remember our rules, we have 2 elements by themselves. So we already know those are going to be 0, right? They're just by themselves. Happen to be diatomic, but that doesn't matter. They're just by themselves. So that's that. If we want to do the next bit, we're going to have to do some algebra. Remember, this is not an ionic compound, so we're going to have to come up with the oxidation numbers ourselves. First, we want to look at fluorine. There's no fluorine. Next, we want to give hydrogen +1. So let's go ahead and do that. And that'll give us enough information to solve this. So we get +1, -3. Remember, always report for one atom. Each hydrogen has an oxidation number of +1. So we are going to report it for that particular atom. So we don't report +3 for the hydrogens, even though there are 3 of them. We say it for one hydrogen. Each hydrogen is +1 for oxidation number purposes. And so we can see over the course of the reaction, nitrogen has gone from 0 to -3. Hydrogen has gone from 0 to +1. Remember that going more negative, reducing your number, making it smaller, like -3 is smaller than 0, that's reduction, right? We are gaining electrons, we're becoming more negative. And on the other side, the hydrogen is getting more positive, it's losing electrons. As a result, we consider that an oxidation. And so yes, because something has changed in terms of oxidation numbers, yes it is. This is a redox combination reaction. Hopefully not too bad. We can look at another one. Let's take one of our favorites. We'll go ahead and heat that. We get calcium oxide and carbon dioxide. We can go ahead and do the oxidation numbers for these as well. This time we have a decomposition reaction. We will find out. And how we do that again is we're going to assign oxidation numbers to all of the components in this reaction, and we're going to see what changes, if anything, over the course of the reaction. So let's go ahead and do it. First thing we see here, this is a compound, and we have in it a simple ion. Calcium is a simple ion. Carbonate is not a simple ion, but calcium is. Remember that simple ions have oxidation numbers equal to their charge. So we already know that calcium is positive 2. We can say that on this side too. In fact, those are both simple ions on that side. So we can go ahead and do those first. Remember, first thing is stuff by itself is 0. Then simple ions, same as their charge. After that, then we look at compounds and try and calculate things. So we know that in this compound, we have a calcium, a carbon, and 3 oxygens that all has to equal 0. We know that calcium is +2, but we don't have enough to solve this quite yet, so we now need to look at carbon and oxygen and decide which of those we have a rule for. Well, rule 4, we start with fluorine, then hydrogen, then oxygen. So since we don't have fluorine or hydrogen, we're going to give oxygen -2. And so doing this, we should get carbon is +4. So oxygen was -2, carbon +4. Okay, hopefully that's all right. The next one we have is carbon dioxide. So we just need to go ahead and do the same thing. Again, we see that we have the rule for oxygen but not for carbon, so we get +4 and -2. And so if we go ahead and take a look at everything happening in this reaction, what was next? Carbon. I'm going to put oxygen twice because we do have 2 oxygen-containing compounds in the products. So just in case one of them was different, even though they aren't in this case, it's always a good idea to put both when you're looking at this. And so, because nothing changes, we call this a non-redox reaction. So this particular one was non-redox. All right, so we're looking at the oxidation numbers of everything in this reaction. I'm going to just underline this as our simple ion, just so you remember that. Don't forget about your simple ions. You might also have noticed that we had a rule for polyatomic ions. And you might be like, well, carbonate's a polyatomic ion. But we don't have just carbonate here, right? We have calcium carbonate. Calcium carbonate is a compound. If we were just looking at the polyatomic ion, then we would set the thing equal to its charge. But since we're looking at a compound, we just do whatever is given to us in the reaction. I think, in some of the homework, you're going to have things like, something like this, where you're using the permanganate ion or the hydroxide ion or something. At that point, then you can go ahead and look at polyatomic ions by themselves. And you'll apply rule 3 and just make everything, you'll say for this one, you'd set it equal to -1. But notice, if we put a potassium with that, now it's a compound, so we have to treat it as a compound. We have to set it equal to 0. And, we're going to see that everything is going to be the same anyway, either way you look at it, but that potassium is there for charge balancing. That potassium gets rid of that -1. This -1 charge is what's taken care of by potassium if we were to put a potassium there. Because potassium is a +1, right? So those two would cancel out. So this is a polyatomic ion. This is a compound. And so it's still rule 3. We still look at them the same way. We add them up and see what we get. For polyatomic ions, it's equal to the charge, but only if you're looking at the polyatomic ion by itself. It's not part of a compound. That's when you use this charge thing. If it's part of a compound, don't worry about polyatomic ions. Treat it like any compound and do it that way. So, last kind of thing I want to let you know is that sometimes oxidation numbers, sometimes they're 0 in a compound, or sometimes you'll see them even as fractions. So fractions are okay as oxidation numbers. If we take an example, this is not quite an ionic compound. It is, but it's one where the ions have different charges. Some of the ions are +2, some of them are +3. And the problem, though, is that we don't have a very easy one to look at. So with this, we would want to go ahead and calculate it. We don't have simple ions here necessarily because we have some weird different ions happening. And we see as a result, we get 8/3 or 2 2/3, whichever way you write it. So this is the average one. So each one is on average +2 2/3. But really, in reality, we might be able to say we have something like this, where we have 2 +3s and 1 +2. On average, that would give us 2 2/3 of a charge each. So the oxidation number would be your average charge. Not very common to see something like this, but it does happen. So we would still list the oxidation number of the iron for this compound as 8/3. Or if you like, 2 2/3. I prefer 8/3, just why bother doing the math? Save yourself the time. So, yeah. So, totally okay. So we can have 8/3 and -2. Those are fine. And you'll see that if you do glucose, that you'll have an oxidation on carbon equal to 0, which is totally fine in a compound. Not a problem. Normally we see 0 when things are by themselves. You could have 0 within compounds as well. All right, and remember, for covalent compounds, these are not charges. They are just ways of keeping track of electrons. All right. So you should be good to go ahead and work on the redox homework. It's coming up. This was just kind of extra practice on it. Do we have any questions on the redox stuff? I'm going to just put a couple of things out. We're going to see that sometimes we can we can use our knowledge to determine if something is redox or not without even doing oxidation numbers. We're going to see that single replacement and combustion reactions are always redox reactions. It's positive because the oxidant is negative. So if you solve this part, 3Fe equals negative 8, positive 8, because this part is negative 8. So to move that to the other side of the equation, you would need to add 8 to both sides. And that's why it's positive. That's also another, I guess, point to make, that if you have a negative oxidation number in a compound, you have to have at least one positive, something to balance it out, right? So not all your oxidation numbers can be negative. They can't all be positive either within a compound. So something's got to be negative, something's got to be positive. We're going to see that double displacements are never redox. Charges do not change in double displacement reactions. They always change in singular replacements and combustions, although combustion doesn't have charges. And then the sometimes ones are combination and decomposition. If you were asked about those, you would need to do redox or oxidation numbers for combination and decomposition reactions. Those ones we can't tell right away if they're going to be redox or not. So 3 of our reactions, though, we will know right away if it's redox or not. If you can identify it as single replacement, it's redox. If you can identify it as double displacement, it's non-redox. Combustion, redox. The other 2, got to do the oxidation numbers. All right, so that's kind of one last little bit here. Okay. For example, let's just do one more. Let's say we do, how about zinc? Single replacement, right? This would be aqueous, yes. Single replacement reaction, redox. We don't need to do the oxidation numbers, but we could. If you wanted to, you would get 0 plus 1 minus 1 plus 2 minus 1, 0. I'm just giving those to you, but you don't need to do them because you can identify it right away as a single replacement reaction. Element plus compound turns into compound plus element. That's single replacement, right? So I want to train yourselves to identify reactions because that can save you work. If you wanted to balance this, by the way, all you need is a 2 here. So sometimes the balancing is very easy for us. So cool. Okay. Let's go ahead and talk about solutions a little bit then. So that's our kind of last little bit. So single replacement, we don't have to do the oxidation numbers. However, if you wanted, you could, and you would still see that it's redox. You'd see that zinc is being oxidized and hydrogen is being reduced in that reaction. All right. Cool. Did you really think we were done with our good friend stoichiometry? Never, unfortunately. We're going to see that, the last time we talked about stoichiometry, last chapter, we were doing things with masses, right? Previously, we had kind of a basic unit plan, right? And this could be actually interchangeable. We could go either direction on this, of course. And we saw that we would use the molar mass to go between the mass and the moles. Sometimes, however, mass is not the easiest thing to use, especially if you're doing some sort of analytical work where you don't quite know something. If you're trying to figure something out, mass is not something that's very easy to use. And so maybe you don't know the mass. So one way that we're going to kind of broach this is that we have a measurement, or rather a measure, of the concentration of a solution. Solute meaning the thing that's dissolved, of course. Just in case we forgot that. So remember, the solute is the thing that's dissolved. So, for example, salt water, the solute is salt. Solvent is water. The solution is salt water. We very often say the molarity of a solution, which is given as capital M, is the moles of your solute, whatever it may be, over the liters of solution. And this is a way of talking about concentration. So concentration tells us how much is dissolved. And so we have a way of describing that. We talk about the moles of solute over the liters of solution. And so something like that might be if I take 50 grams of salt, sodium chloride, and dissolve it to 500 mLs, we can figure out its molarity. For molarity, we need moles and liters. However, here we're given grams and milliliters, so we don't quite have the right units. So we're going to see which one makes more sense to go to moles and which one makes more sense to go to liters. Hopefully, we can see right here, that's the one that should go to liters, right? We have milliliters already. It's a lot easier to go to liters of that. And since the other part we need is moles, we need to convert that into moles. So we already know how to do these, right? One is just a metric conversion. The other one is using the molar mass. So for our moles, we're going to have 50 grams. Mole on top. 58.44, I think, on the bottom. Molar mass of sodium chloride. Bust out thy calculator. 50 divided by 58.44. 0.855578. 3 sig figs there. Oh, that's something I've been meaning to talk about. Y'all keep forgetting your sig figs. So the biggest mistake I see on your homework is that sig figs are just ignored completely. We spent all this time learning them. We did homework on doing sig figs. And then the very next homework, about 2/3 of you just threw the sig figs out the window and just gave me answers like this with, you started with 3 sig figs, you ended with 6 or something. It's, don't forget your sig figs. It's easy points to lose, so it's just better if you don't. Remember that we have to always apply sig figs. I'm going to write that in purple. Always keep doing sig figs. 4 exclamation points. No, I'm sorry, that's 5. I can't even count them. Don't forget your sig figs. Alright, so anyways, that's our moles of sodium chloride. Again, I'm giving a few extra decimals so that I don't lose track of my accuracy. And I'm still going to note that I really only have 3 sig figs in that number, and the rest are just not rounded yet. For our milliliters of solution, that one's an easier one to go ahead and do. And so, as a result, we get 0.5 liters with still 4 sig figs. Do not forget your sig figs. This had 3 sig figs. This should have 3 sig figs, but we're not done yet, so we're going to keep that. This is 4 sig figs. This is 4 sig figs. Don't forget that either. All right, so the molarity of this solution is going to be our 0.85578 moles over 0.5 liters. And so, as a result, at the end of this, calculator time, we get 1.71156. You can leave it as capital M or moles per liter. Either way is fine. Capital M is a unit which stands for moles per liter. But wait, we didn't do our sig figs. So we need to give our answer as 1.71. Because of the 3 sig figs. So 3 sig figs over 4 sig figs. Choose the smaller number, that's 3 sig figs. So don't forget your sig figs. Alright, so our answer there was 1.71 molar. What's more useful about this, it's all fun to calculate, right? Just need to have things in moles and liters to calculate this. But this is now a conversion factor. Notice 2 units, moles per liter. That tells us how many moles is equal to how many liters of solution. And this is something that's a lot easier to measure than masses, especially if something is unknown. And so this is going to be very useful for us because now we can say we've done this sort of idea. So just putting out what we've done already. Do not forget we had, of course, in the middle our reaction coefficients. But now we're going to add to our fun kind of chart here. We now have another way to talk about moles of A. We can say liters of A solution. We can use the molarity of A, whatever that happens to be, if we're dealing with a solution. We can go between liters and moles by using the molarity. And guess what? We can also go, same thing for B, assuming it's a solution. And so we can go whatever way we want with this. We can say, okay, well, I need to go this path. I need to start with liters of A and end up with mass of B. I'm going to start with liters of sulfuric acid and find out how much sodium sulfate I get out at the end in grams. That's totally something we can do here. Or I'm going to start with liters of solution and I'm going to end with liters of solution. And I'm going to do this pathway. Notice again, the middle part is still that reaction coefficients idea. The stoichiometry of it is still the same. I can go still mass 2 liters. I can do any of these. These are pathways. Pathways with reversible arrows, so you can go whichever way you need to go. So let's take a look at what that might look like. What volume is, of, let's see, 1.25 molar Now, we can say what volume of this solution is needed to react with this mass of some other substance. So, we see here, we have, this would be our mass of A, and we're looking for volume of B. I guess technically liters of B is what I had written there, but we're looking of that, right? A, we always choose the one we know the most about. Can we get moles of sulfuric acid right away? No, we just have the conversion factor. We don't have any number associated with it. But 5 grams is something we do know, so that should be A. Again, it doesn't really matter though, but I usually put A as what I know the most about. So we have a mass A, and we're looking for volume of B. So this is our unit path. We're going from the mass of A, sodium hydroxide, to going to moles of that using the molar mass. We will then use our reaction coefficients to go from sodium hydroxide to sulfuric acid. And then finally, once we have moles of sulfuric acid, we can use its molarity to give us the liters. And then since I asked for milliliters, we'll just have one last little conversion at the end to do. But that's what we're doing right now. So we already have our plan. We already have our plan here. So we're starting with grams of NaOH. We're going to moles of NaOH, to moles of sulfuric acid, to liters of sulfuric acid, to milliliters of sulfuric acid. I just ran out of space there. I'm going to actually, I'll put ml up here. Why not? And it was only because if I asked you for milligrams or something, I mean, I could have given you milligrams instead. We'd still need to convert it to grams first. So it's really, the only thing new here is this idea of concentration. I'm giving you a conversion factor. And so it's just up to us to use it. So let's look at all those conversion factors. Every arrow in your plan is a conversion factor. To go from grams to moles of a substance, like we've seen previously, is the molar mass of sodium hydroxide, which is just about 40. And again, that's just a number I happen to know, but we're okay with that. The next one is our reaction coefficients. We don't have those yet because we haven't written out our reaction and balanced it. Going between moles and liters of solution, that's using molarity. We're given that it's 1.25 molar, or moles per liter. And then the last one is just liters to milliliters. And that's just a metric conversion. So we already know that one. So we don't have conversion factor 2 because we haven't written out a reaction yet. All right. What type of reaction is this? Excuse me. Coffee down the wrong pipe. Oh no. What type of reaction do we have here? And how do we know? What type is this? We have 5 types only. Is this a combustion reaction? I hope not. What type of reaction is 2 ionic compounds reacting together? Knock, knock. Are we awake in there? Take a guess. You have a 1 out of 4 chance now that we've gotten rid of combustion as an option. Yay! Michaela wins. It is indeed double displacement. 2 ionic compounds coming together. That means it's double displacement. This is a double displacement reaction. Absolutely. So we know that we need to just split up our ions, and we'll go ahead and form the correct products. So we'll get, I'll just do it for us. This is happens to be a neutralization reaction, right? We're producing water that's liquid. For balancing purposes, we're going to need 2 of these and 2 of those. But now we're okay. That's what we needed. We needed our coefficients. So we don't need to do anything else here. We only needed to write this out to get our coefficients so that we had our second conversion factor here. So now that we have it, now that we know we have 1 mole of sulfuric acid for every 2 moles of NaOH, now we can go ahead and do all this. So I don't even remember how much sodium hydroxide to be at. 5 grams. Okay. So 5 grams. We're going to have 40 grams, which is the molar mass. Notice again, I'm being very specific about what substance I'm doing at each time. So sodium hydroxide first. Next, we need our reaction coefficients. We have 2 moles of NaOH. That's our coefficient in the reaction. 1 mole of sulfuric acid. Oh no, we're going to run out of space here. Next, we need our molarity, 1.25 moles per liter. So we'll put the 1.25 moles, 1 liter. And since I had run out of space, we'll just put this there. For liters, we have 10 to the negative 3 liters, 1 milliliter on top. And then we can go ahead and, I guess I need to move this over a little bit. And we'll get our answer out. So, again, your friend, use it. 5 divided by 40, divided by 2, divided by 1.25, times 1,000, equals, oh, I have a mistake. I did 5 times 40. Okay, so hold up. Okay, 5 divided by 40, divided by 2, divided by 1.25. Now I can do times 1,000. There we go. So I got 50. Where am I finding the last two conversion factors? This one is given in the problem. That's this number here. Remember that molarity is our conversion between moles and liters. That's the conversion factor right here. We're going between moles of B and liters of B. The last conversion factor is definitely something we should know. That's just a metric prefix. This one should be, at this point of the semester, should be pretty solid. Milli and base unit conversion should be pretty solid by now. So don't forget your metric prefixes there. You know, like nano and stuff I get we don't use very often, but milli we've been using all the time. So don't forget that one. All right, so with this, are we done? We are never done because sig figs must always be applied, right? Let's look at the numbers we're given. Numbers that we're starting with in our problem, the numbers that we're starting with are the 1.25 and the 5. So we need to decide which of those has the smaller number of sig figs. They're both 3, so our answer should have 3 sig figs. So don't forget that. So we're going to need 50 mLs. That turned out to be quite a nice number, didn't it? How curious. Didn't intend for that to happen, but whatever, worked. So, new things here. There's only one new thing. The only new thing here is just remember, molarity is a conversion factor. Molarity is our conversion factor between moles and liters of a solution. We'll see that we are going to have a different one. We're talking about moles and liters of a gas, but this is of a solution. I'll put that in parentheses. And so anytime you're dealing with a molarity, you would need to be given it, right? Because I can make a solution of whatever molarity I want by dissolving more or less of my particular solute in it. If we saw that by dissolving whatever amount of salt, I ended up with 1.71 molar solution, I could dissolve less, I could dissolve more. I can choose the molarity I want to work with when I'm in the lab making solutions. But in problems like these, you'll either be given a molarity or you're asked to find it. And so that's the only kind of thing here. The molarity is not something that we can just look up. Like molar mass is something that we can look up, right? Because it's just on the periodic table. It's constant. Molarity depends on how much is dissolved, right? And that's totally something we have control over. We don't have control over the molar mass of a substance, but we do have control over how our solutions are made. And so this number would have to be given to us, or we would have to be given enough information to figure it out. And indeed, that's one of the more common laboratory experiments that we would do around this time, is using molarity of a known concentration to find molarity of an unknown substance's concentration. Let's take a look at that. This is a skill called Volumetric Analysis, also known as titration. You'll have a lab simulation on this soon enough. Actually, I think I have it for you already. I don't remember. I put up a couple last night. Basically, you use a known volume and concentration of a solution to react with an exact volume of a solution of unknown concentration. Oftentimes, finding out the concentration of something is very important. As I am now dealing with, so I just moved to a place with a pool, and I have to deal with figuring out all the various pool chemicals, like the concentration of chlorine and all that. And in lieu of doing titrations, they use little like test strips that have different colors. But if I were to really go crazy, I would bring my pool water in and perform titrations on it to figure out the concentration of various components of these solutions. And so it's an analytical method, a method of finding out something. And it's very important that these are done kind of accurately, because you're looking for an unknown, and oftentimes, you want to be as exact as possible in determining that unknown. For example, let's say you get pulled over for drunk driving. Shame on you. But if you do that, if you say you refuse the breathalyzer, which you generally should, you will end up being taken to either the police station or somewhere where they're going to take a sample of your blood and titrate it to figure out the ethanol concentration in your blood. And so they will use an exact volume of your blood, however much they need. They will use a known concentration of some other solution, and they're going to react that until all your ethanol has reacted in your blood, and then they're going to know exactly, they're going to be able to calculate how much was in your blood and say, okay, you're below 0.08, so you're good, or you're above and now you're going to jail. So one of the two. So it's a very practical method. It's absolutely used all the time in real life. Forensic chemistry. Oh my god. Calvin's outside barking and causing them all to bark. Oh well. Okay, anyways, so let's see how this looks. So we will know that we have, exact volume of mystery. Hold on, let me go get Bo, because he's going to start barking. Bo, come here. Come here, buddy. Alright, we have the instigator here. Okay, so we're going to have an exact volume of beef that we will have chosen. We will have said, okay, we know exactly how much of this volume we have. We do not know the concentration of beef. So this is, again, something you would set up in lab. You say, okay, well, I have this unknown solution. I'm going to measure out exactly 20 mLs of this so that I know exactly how much volume I have. We're going to see that we have exact concentration of some other solution that we are testing it against. And so, laboratory-wise, we will measure the volume, the volume of A needed to react. Very often these reactions do have 100% yield or very close to it, and so we can kind of skirt a way around it. But by knowing these two exactly, and by measuring very precisely how much volume of A we had, we can figure out the concentration of B with good accuracy. What's our time, by the way? Oh, it's only 10:30. Okay. Often this is done using an instrument called a burette. This has a little... Hi, buddy. Okay, I'm going to put you down if you're going to be good. Okay. A burette is the instrument you would use to figure out that measurement of volume of solution A. You would put it into this burette. And the burette is always read to 2 decimal points because that's the way that the burette is written. So you'll have, say, 20 mLs, 21 mLs. Obviously, actually these are often written upside down, but we won't even worry about that yet. So these have graduations for 20.1, 20.2, 20.3. And remember, we read those one more decimal point than we know for sure. And so we often get, will get 4 sig figs from these. Because you'll read them to 2 decimal points. So very often that'll give us 4 sig figs. So that's a good amount for something that we're just using we're not using machines to do this work. We're doing it ourselves. So 4 sig figs is pretty good. That's a pretty good number to get. So that's practically how this is done, but let's look at it theoretically. Let's use the same reaction. To titrate 20 mils of NaOH of unknown molarity in the lab, you would actually measure this. And you would have your already previously known concentration of sulfuric acid. And again, notice all the sig figs we have there because that one has previously been titrated, we'll say. And so we already know that. And so now we have enough information to figure out this process. We know, thankfully, because I'm using the same reaction, we know, in terms of moles, how many moles of sulfuric acid need to react, or how many moles of sodium hydroxide are needed to react with a certain number of moles of sulfuric acid. And so we can use the volume and molarity of sulfuric acid to determine how many moles in the sample. Another word you'll see, by the way, is called aliquot. An aliquot is a sample. Just means the same thing. Remember that if we want to find concentration is moles per liter. We need moles, right? We have liters of sodium hydroxide already. We just need the moles. So we can use the information we got from sulfuric acid to figure out the moles, because we know how many moles of each need to react together, right? So if we're looking for moles of NaOH, and we're starting with, I guess, milliliters of sulfuric acid, we just need to work through it, right? We know in order to go to moles of NaOH, we have to have moles of sulfuric acid. We can only do it moles to moles. We have to go from moles of one substance to moles of another substance. There's no other way to go from anything about sulfuric acid to anything about sodium hydroxide. We have to go through moles. So, our last little bit here, we just will need liters instead, because molarity is our conversion between moles and liters. This one's just a metric conversion. And again, this is our reaction coefficients. So we already know all of our conversion factors. And so we have our milliliters, we have our molarity, we have our reaction coefficients. Let's do it. We see that we have, I've already forgotten, 22.16. If we need this in liters, we're going to use our metric system prefixes. Same as before. We need milliliters to cancel out. Milliliters goes on the bottom. Notice again, by the way, all this stuff is still just unit conversion. That's all it ever is. That's all chemistry is about. So next we're going to use, so that's our metric part. We're going to use our molarity, which was 0.4262. Remember that molarity is moles over liters. So the 0.4262 goes with moles and 1 liter of sulfuric acid. And then the last thing we need is we're going to have our reaction coefficients. And so doing this math, here we go. Always do this with me just in case. Times 2. I get 0.018889184 moles of sodium hydroxide. With this, it looks like we need 4 sig figs, so we'll keep that in mind, but I'm going to still keep all my numbers. And that is the amount in our sample. Our sample was 20 milliliters. We now have moles. If we want to find molarity, remember molarity is moles over liters. So moles of sodium hydroxide over liters will give us our molarity of sodium hydroxide solution. Not too bad. And so that should be 0.01888 9184 with 4 sig figs divided by 0.02 liters. Again, I'm just doing that milliliters to liters, something you should be at this point able to do in your heads, I would hope. Or at least use your calculator. 20 mils is 0.02 liters, so just keeping the same sig figs. So with that, we do this, we get 0.94444592. Both of our numbers had 4 sig figs that we're dividing here. And so as a result, 0.9446. Nope, 5. I don't know how to read. So we're able to figure out our concentration of sodium hydroxide pretty exactly, pretty accurately. Look at that. We got it to the 0.0001 significance. So burettes are very useful tools for us as chemists using analytical chemistry like this to determine something of interest. In this case, it's the concentration of a particular solution. All right, so this was our problem. We had an exact volume of mystery solution B. We had an exact concentration of solution A, and we figured out, again, I'm giving you the numbers because obviously we're not in lab right now, but we somehow found out that we needed 22.16 milliliters of this solution to react. And so as a result, we were able to calculate the concentration of our unknown solution by figuring out the moles we had and then using the amount of volume we had for our sample. And so we ended up with this number. Fun stuff, huh? So, but really it's more of the same thing. We're just throwing in one or two more, actually just one concept here. The conversion between moles and liters. Molarity. It's concentration. We can talk a little bit about how to make solutions as well, how to come up with these molarities. There's two things we need to know to make a solution. We need to know the desired molarity and the desired volume. We need to know how concentrated we want our solution and how much of it we want. Right? I mean, it doesn't make sense to make something if we don't know, if we don't have these things in mind, right? So, I mean, this is something you already know potentially how to do, at least at a basic level. Say you like your coffee sweet. You already know how much coffee you want. That's your desired volume. And you probably have a pretty good idea of how much sugar you want to put in there to make it to your desired sweetness. That's the concentration of sugar. So you already have this idea in your mind about how much solute, something to dissolve, you're going to be putting into your solutions to get the exact volume. You know, if you're at Starbucks, you get a tall, you're going to need less sugar than if you got a venti, right? Because the concentrations or the volumes are different. So you're going to need more solute to get your desired concentration. And so we need to just know these two things. And so we have two options after this. Option 1 is dissolve the solid. Or option 2 is dilute a solution. Solution. Those are our two options for making solutions, keeping in mind that we want these things. So let's say I want So let's say I want 1/4 of a liter of 1 molar sodium chloride. Pretty straightforward question. How much sodium chloride do I need in grams? Well, we're in this case, if we go way back up to our chart of fun stuff, wow, that chart is way up here. Making a solution is just doing this bit if you're dissolving a solid. Mass of A, molar mass of A, moles of A to liters of A. In this case, we're starting with liters. That's the amount we know. We know we want 0.25 liters. And we know what molarity we want. And as a result, we know how many moles we're going to need. From knowing how many moles we need, we can get the mass of that by using the molar mass. So we're starting here, and we're ending here. So we're just following this path. In this case, it's the same substance because we're not doing any chemical reaction. There's no coefficients here. We're just dissolving something. So let's take a look. Oh my goodness. So we know from there, we can go from volume, let's say liters, to moles, from moles to grams, using our molarity to go from liters to moles. That's what molarity does. And then we need our molar mass. So let's go ahead and do it. We have 1 molar. 1 molar means 1 mole per liter. Remember the one with all the decimals, the molarity number goes with moles, always 1 liter. And then we need the molar mass, which I think was 58.44 grams for 1 mole. And so 0.25 times 58.44 gives us 14.61 grams. And that's already 4 sig figs, which is what we needed anyway, because our 0.2500 liter and 1.000 molar are both 4 sig figs. So we're going to need to measure out 14.61 grams. And how this will work is very often, you can't just say, I'm going to put 250 mLs of water in there, or 0.25 liters of water. That's not how it works, because the sodium chloride does have a small volume. So you can't just add and call it a day. You have a piece of glassware that we're going to use called a volumetric flask. Oops. Oh my gosh. These have a very specific line on them when you're filling them up. And each volumetric flask measures 1 volume only. If you have a 10 ml volumetric flask, you are going to be, that line tells you exactly where 10 mLs is. If you are using a 1 liter volumetric flask, that tells you where 1.000 liters is. For us right now, it's a better idea to use a 250 ml volumetric flask. These often have 4 sig figs as well. So this line tells us exactly that volume. So we are going to first put our solid in there, all of those salt bits. The sodium chloride goes in, and then we are going to fill up to the line with water, with deionized or distilled water. So the sodium chloride goes in, And then we fill up to the line with deionized water. Deionized water just means it's essentially pure water. We've gotten rid of all the stuff in the tap water. Tap water has all these calcium and magnesium and chlorine and all that. So we have to deionize our water so it's pure, so that we end up with just what we want. So we're going to put our sodium chloride in, we're going to fill it up to the line, and we're going to have exactly 250 mils of solution. Remember that molarity is moles over liters of solution, not liters of water, liters of solution. So you're going to weigh out your mass of your substance. In it goes. Then you're going to add water up until that line. And then you will have your exact volume of your solution of exact molarity. Pretty nice process there. The option 2 was dilute a solution. Sometimes if you're making a lot or frequently making different solutions of the same compound, it helps to have a concentrated solution. And then you can just dilute it. It's a little bit easier. With this, you're going to have what's called a stock solution. So that one will have been previously made and it will have a high concentration. So it's concentrated. And so what we can do with this is understand that in a solution, we can always just add water, right? If I have 5 molar sodium chloride, that means there's 5 moles of sodium chloride dissolved in 1 liter of water. If I add 4 more liters of water to that, I will now have a 1 molar solution, because now I have 5 liters of solution, but still only 5 moles of solute. So we're going to see that your moles of solute is still the same. And so it's very often easier, especially if something only comes as a liquid, to just do it volumetrically. So I'm going to write out that example. So I had 5 molar If I add 4 liters of water, I'm just going to say 5. Ideally, fine, I'll go ahead and do this. So we'll put all of our sig figs in there so everyone will be happy. Okay, there we go. So if you have a concentrated solution and add water to it, you can dilute it. Pretty straightforward. The moles don't change of your solute. We're not changing how much sodium chloride is there, we're changing the amount of water. And so we have a formula. I know all of y'all love formulas. So this is your molarity and volume of kind of your first solution, whatever it may be. That might be your stock solution or your desired solution. And then that's the molarity and volume of solution 2. And so here we might say, okay, well, I had 5 molar sodium chloride, and I had 1 liter of that. That's what I started with. To find out the new concentration, we don't know the concentration, but we know our new volume is 5 liters. And so as a result, solving for M2, we get 1 molar. So I diluted my solution. But let's do another example. Let's say I want to make that same solution from before. So I want 0.25 liters of 1 molar sodium chloride. So I want same thing as before. Now we can say instead of massing out our sodium chloride, we can take our stock solution and just dilute it. And so our desired ones could be solution 1. In this case, we're looking for how much, so it's a volume, times 5. So V2, divide this by 5, we get 0.05 4 sig figs liters of this. And so, that's the same thing, by the way, 50 milliliters. And so our process here would be, we would measure 50, oops. We would still use our volumetric flask here, by the way. And then we would add water up to the line. Oh my gosh, why have I still not blocked that spam? Someone please remind me to do this later. Go away, big follows, people. I'm popular enough. Okay, so it's the same idea here, but now we can calculate how much volume of a stock solution we'd need. We would still put it into our volumetric flask, and we would add water up to the line. If you were to just add 200 mils of water for this case, it'd probably be fine because we have nice volumes here. But sometimes like your volume ends up being like 6.42 mLs of stock solution or something. And so it's a little bit harder to say, okay, well, I need 250 minus that, and just easier to fill up to the line rather than trying to measure out the exact volume you need. So this is the best kind of practice for that. So 2 options there to make a solution. And the last thing I want to kind of touch on is that, here we'll say, if we just take a look at a solution in terms of its concentration, this is the same thing as saying this. You might be like, well, what the hell? Where did this come from? Remember that an ionic compound that's soluble will fully dissociate because it's a strong electrolyte. And so it may be important for us to know the concentration of chloride ions in a particular solution. So we just have to remember that this thing is really 1 calcium ion and 2 chloride ions. So if we have 1.25 molar calcium chloride, we have twice that amount of chloride ions because we have 2 chlorides per calcium chloride. So as a result, we have twice as much at the end there. So that's one last thing to keep in mind, is so oftentimes maybe we're just looking at concentration of one ion. That can be different from concentration of your solution. For calcium ions, it's the same. They're both, it's a 1-to-1 thing, but the chloride we have twice as much. So that's kind of that. All right. So we'll just end here today because we're done with chapter 4. We'll start chapter 5 on Wednesday. Chapter 5 has a lot of math. It is our most math-intense chapter in the course, so be mentally prepared for that. It's also a fairly long chapter, so there's going to be a lot of different concepts and a lot of math going on with it, so you may want to mentally prepare yourself for that. So at this point now, you are able to do, you can do all of the double displacement, the redox, and the molarity homework. Don't forget sig figs. Just for the homework, don't forget sig figs. And also just keep in mind, I've had people emailing me telling me they've put comments on things on their homeworks. I don't see those unless I'm actively scrolling through your homeworks. So just remember that Canvas doesn't inform me about comments on homework. So instead of, so sometimes I'll put a comment on your homework. Often, remember, I don't, just because 300 homeworks a week takes a long time to grade, right? So Canvas doesn't tell me if you comment on something after I've already graded it. I'm not going to go back and look at these things again. So if there's a problem, or if you're like, hey, why did I, do this? First step is check the key, the homework key. Check the key. You should always be doing that as soon as I post the key, by the way. You should be checking your answers with the key. Always, always do that. And then you can message me on Discord or Canvas or email, whatever. Those ways I will see them. If you put it on a comment, I will have no idea it exists. So I'm not ignoring you. I would never mean to ignore you. But just be aware of that. I don't get notifications if you put comments on your homework on Canvas. So I have no way of knowing if you've ever written me something. So I just wanted to put it out there that I'm not ignoring you on purpose. I just don't know that you've written anything. So, and yeah, I'm not going to be spending all my time just scrolling through your homework hoping someone's put a comment. So, Okay. So first thing, always check the key. See if you can figure out what went wrong on the homework. And then secondly, if you have no idea, you can message me. Chances are, by the way, I'm going to say sig figs is the reason that you got 9 out of 10 or whatever. So that's something that's always part of your homework. All right. Cool. So you're up to date on those. We're going to start thermochemistry on Thursday. Long chapter, lots of math. Be mentally prepared for that. And then I can also post some information about averages on the exam and all that, so you can have an idea of how you're doing. Okay? Alrighty then. See you all next time. Enjoy your day. See you on Thursday. Take care.